take a look at the functions and their graphs. Let's analyze the graphs. If we draw these graphs with a pencil, then we see that the first two graphs cannot be drawn without lifting the pencil. While the third graph can be drawn without lifting the pencil. It means that the first two functions are not continuous, while the third function is a continuous function. Mathematically, a function is continuous at x is equal to c if the function is defined at x is equal to c, and the value of the function at x is equal to c is equal to the limit of the function at x is equal to c. Now, let's interpret these graphs by determining the left and the right-hand limits of each function. Let's start with the first graph. It is clear that the value of the function is equal to 2 for all negative values of x. This implies that at all points near and to the left of 0, like minus 0.01, minus 0.001, minus 0.0001, and so on, the value of the function is 2. Thus we can say that the left-hand limit of f at 0 is 2. Similarly, at all points near and to the right of 0, like 0.01, 0.001, 0.0001, and so on, the value of the function is 3. Thus the right-hand limit of f at 0 is 3. The value of f at x is equal to 0 is 2. Observe that the left-hand and right-hand limits do not coincide. Also observe that the value of f at x is equal to 0 coincides with the left-hand limit. Therefore, the function is not continuous at x is equal to 0. Next, consider the graph of the second function. In this case, the left-hand limit and the right-hand limit of function f are both 2. However, the value of the function at x is equal to 0 is 1. Here also, the value of the function at x is equal to 0 is not equal to the left-hand limit and the right-hand limit. Hence this function is also not continuous at x is equal to 0. Now observe the third graph. In this graph, the left-hand limit, the right-hand limit, and the value of the function at x is equal to 0 are all equal to 1. Hence we can say that function f is a continuous function at the point 0. Let's phrase the definition of continuity. Suppose f is a real function on a subset of real numbers, and c is a point in the domain of f. Then f is continuous at c if the limit of f of x as x approaches c is equal to f of c. If f is not continuous at x is equal to c, then we say that f is discontinuous at c, and c is called a point of discontinuity of function f. Let's apply the definition of continuity to check the continuity of a function f given by f of x is equal to 3x plus 1 at x is equal to 1. It is clear that the value of the function is 4 when x is equal to 1. Next, we'll find the limit of the function as x approaches 1. This is given by limit of 3x plus 1 as x approaches 1. This is equal to 4. Thus, the limit of the function coincides with the value of the function. Hence, the function is continuous at 1. Let's now check the continuity of function f of x as shown at x is equal to 2. From the definition of the function, it is clear that the value of the function at x is equal to 2 is 6. Next, the limit of function f of x as x approaches 2 is equal to 7. Here, we see that the limit of the function and the value of the function at x is equal to 2 do not coincide. Hence, the function is not continuous at x is equal to 2. Let's now check the continuity of the function f of x. Let's now check the continuity of the function f of x is equal to sin x in the closed interval 0, pi. The graph of the function in the closed interval is shown. It is clear from the graph that the function is continuous at every point that lies between 0 and pi. However, if we say that function f of x is equal to sin x is continuous in the closed interval 0, pi, then we need to show that it is continuous at every point in that closed interval. So let's check the continuity of the function at its endpoints. The right-hand limit of f of x at x is equal to 0 is 0, which is the value of the function at 0. The left-hand limit of f of x at x is equal to pi is also 0, which is the value of the function at pi. Hence, the function is continuous at the endpoints. Here, we do not need to find the left-hand limit of the function at 0 and the right-hand limit of the function at pi. This is because the points left to 0 and right to pi do not lie in the given domain. Thus, mathematically, a real function f is said to be continuous if it is continuous at every point in the domain of f. Let's study the nature of the function. F of x is equal to 1 divided by x as x approaches to 0 from the right. That is, we intend to find the right-hand limit of the function f of x at 0. This table shows the values of f of x for different values of x. When x is equal to 1, f of x is also equal to 1. The value of the function at x is equal to 0.5 is 2. The value of the function at x is equal to 10 raised to the power minus 1 is 10. The values of the function at other points are as shown. Observe that the value of the function increases as the value of x comes closer and closer to 0. This implies that, for a positive real number very close to 0, the value of the function will be a large number. This number is larger than any given real number, which is represented as shown and is read as plus infinity. Therefore, the right-hand limit of the function as x approaches 0 is plus infinity. Plus infinity is not defined. Hence, we can say that the right-hand limit of the function f of x at 0 is not defined or does not exist. Now, let's check for the existence of the left-hand limit of the function at 0. Let's discuss the nature of the function. F of x is equal to 1 divided by x as x approaches 0 from the left. Let's observe the table that shows the values of the function at negative values of x. Observe that the value of the function decreases as x comes closer and closer to 0 from its left side. This implies that for a negative real number very close to 0, the value of the function will be a very small number. This number is the number smaller than any given real number, which is represented as shown and read as minus infinity. Therefore, the left-hand limit of the function as x approaches 0 is equal to minus infinity. Minus infinity is not defined. Hence, we can say that the left-hand limit of the function f of x at 0 is not defined or does not exist. The graph here depicts the graphical representation of function 1 divided by x. Observe that the graph of the function is very close to the y-axis as the value of x approaches 0 on either side of the y-axis. Let us now consider another function. F of x is equal to tan x. The table here shows the values of tan x for different values of x close to 90 degrees from its left side. It is clear from the table that the value of tan x increases largely when the value of x approaches close to 90 degrees. This implies that for an angle very close to 90 degrees from the left side, the value of the function will be a large number. This number is a number larger than any given real number and can be represented by plus infinity. Thus, we can say that the limit of tan x as x approaches 90 degrees from the left is equal to plus infinity. Take a look at this table now. It shows the values of tan x with respect to the values of x close to 90 degrees from its right side. It is clear from the table that the value of tan x decreases largely when the value of x approaches to 90 degrees from the right side. This implies that for an angle very close to 90 degrees from the right side, the value of the function will be a small number. This number is smaller than any given real number and can be represented by minus infinity. Thus, we can say that the limit of tan x as x approaches 90 degrees from the right is equal to minus infinity. Hence, the limit of tan x as x approaches 90 degrees does not exist. Consider two real functions, f of x and g of x, continuous at real number c. What can you say about the continuity of the sum, difference, product and quotient of these functions at x is equal to c? Let's begin by checking the continuity of f plus g at x is equal to c. We are given that f of x and g of x are continuous at c, which implies that both f and g are defined at c, and hence their sum is also defined at c. Now, let's find limit of f plus g of x as x approaches c. By the addition property of the algebra of functions, f plus g of x is equal to f of x plus g of x. Also by the algebra of limits, we know that the limit of the sum of two functions is equal to the sum of their limits. And this is equal to f of c plus g of c. Since functions f and g are continuous at x equal to c. Again, by the property of addition of two functions, it can further be written as f plus g of c. This means that the limit of the sum of the functions is continuous at x is equal to c. Hence, the sum of two continuous functions is continuous at x is equal to c. Now, let's check the continuity of the difference of two continuous functions. As f of x and g of x are continuous at c, we have that f of x and g of x are defined at c. Hence, the difference of the functions f of x and g of x is also defined at c. So the limit of f minus g of x as x approaches c can be found. Therefore, f minus g of x can be written as f of x minus g of x. Now, by the theorem on limits, we know that the limit of the difference of two functions is equal to the difference of their limits. So we have limit of f of x as x approaches c minus limit of g of x as x approaches c. Now, since functions f and g are continuous at x is equal to c, we have f of c minus g of c. This is equal to f minus g of c. By the property of subtraction of functions, this means that the limit of the difference of the functions is continuous at c. Hence, f minus g is continuous at x is equal to c. Let's now check the continuity of the product of real functions f of x and g of x continuous at real number c. As f of x and g of x are continuous at c, f of x and g of x are defined at c. Hence, their product is also defined at c. So the limit of f into g of x as x approaches c can be found. Now, by definition, f into g of x can also be written as f of x into g of x. By a theorem on limits, we know that the limit of the product of functions is equal to the product of their limits. So we have limit of f of x as x approaches c into limit of g of x as x approaches c. We are given that functions f and g are continuous at x is equal to c. So the limit of f of x as x approaches c is f of c, and the limit of g of x as x approaches c is g of c. By the property of multiplication of functions, we get f into g of c. This implies that the limit of the product of the functions is continuous. Hence, f into g is continuous at x is equal to c. If function f is a constant function and is equal to k for some real number k, then the product of functions f of x and g of x is equal to k into g of x, which is equal to k into g of x. Since k is a constant and g of x is a continuous function, their product is also continuous. The product of a real valued constant and a continuous function at some real number is also continuous. If k is equal to -1, then -f is also continuous. This implies that the negative of any continuous function is also continuous. Lastly, let's check the continuity of the quotient of two real functions f of x and g of x at x is equal to c. As f of x and g of x are continuous at c, f of x and g of x are defined at c. Hence, the quotient of the functions f of x and g of x is also defined at c, provided g of c is not equal to 0. Now, by definition, f divided by g of x can also be written as f of x divided by g of x. By a theorem on limits, limit f divided by g of x as x approaches c is equal to limit of f of x as x approaches c divided by limit of g of x as x approaches c. Since functions f and g are continuous at x equal to c, the limit of f of x as x approaches c is f of c, and the limit of g of x as x approaches c is g of c. By the property of quotient of functions, this is further equal to f divided by g of c. Hence, f divided by g is continuous at x is equal to c, provided g of c is not equal to 0. Suppose f is a constant function defined by f of x is equal to k, where k is a real number. Then f of x divided by g of x is equal to k divided by g of x, which is also continuous. Hence, we can say that a real valued number divided by any continuous function at some real number is also continuous. If k is equal to 1, then 1 divided by g of x is also continuous. That is, the reciprocal of a continuous function is also continuous. The derivative of a real function f at point c in its domain is defined as the limit of f of c plus h minus f of c whole divided by h as h approaches 0, provided the limit exists. The derivative of f of x at c is denoted as f dash of c, or d by dx of f of x at c, or commonly as f dash c. Thus, the derivative of f of x is defined by f dash x, which is equal to the limit of f of x plus h minus f of x divided by h as h approaches 0, provided the limit exists. Many a times, a function is defined as y is equal to f of x. For such functions, the derivative of the function is denoted by y dash or dy by dx. Differentiation is the process of finding the derivative of a function. Mathematically, we read f dash x as derivative f of x with respect to x. While defining the derivative of a function at a point c, we always emphasize the fact that the limit must exist for the existence of derivative. In the counterpart, if the limit does not exist, then we say that the function f is not differentiable at c. In other words, a function f is said to be differentiable at point C in its domain if the left-hand limit and the right-hand limit of f of c plus h minus f of c whole divided by h exists and are equal. This definition can be extended to any closed interval a comma b. A function f is said to be differentiable in closed interval a comma b if it is differentiable at every point in the interval and also at the endpoints a and b. The derivative of a function at point A is called the right-hand derivative, and the derivative at point B is called the left-hand derivative of the function. A function is said to be differentiable in open interval a comma b if it is differentiable at every point of the interval. Let's now prove an important theorem which states that if function f is differentiable at point C, then it is also continuous at that point. Let's begin with the proof. It is given that function f is differentiable at point C. This implies f dash c exists and is equal to the limit of f of x minus f of c divided by x minus c as x approaches c. For x is not equal to c, the numerator f of x minus f of c can be written as shown. Now, let's take the limit on both the sides when x approaches c. By using the algebra of limits, we can write the limit of the product of two functions on the right-hand side as the product of their limits. The limit of f of x minus f of c divided by x minus c as x approaches c is f dash c, and the limit of x minus c as x approaches c is 0. Thus, the right-hand side becomes 0. This implies the limit of f of x as x approaches c is equal to the limit of f of c as x approaches c, which is equal to the value of the function at c. Hence, function f is continuous at x is equal to c. Hence, in general, we can say that all differentiable functions are continuous. However, the converse is not always true. Let's verify this with the help of an example. Let's look at the function defined by f of x is equal to modulus of x minus 1. Observe that this function is continuous at x is equal to 1. The given function can be written as shown. Now, to check the differentiability, we have to first evaluate the left-hand derivative and the right-hand derivative at c is equal to 1 as h approaches 0. The left-hand limit of f of 1 plus h minus f of 1 divided by h as h approaches 0 is equal to minus 1, and the right-hand limit of f of 1 plus h minus f of 1 divided by h as h approaches 0 is equal to 1. Clearly, the two limits are not equal. Hence, modulus of x minus 1 is not differentiable at 1. Hence, we can say that all continuous functions need not be differentiable. Let's find the derivative of the function f of x is equal to x minus 3 whole cubed. First, we'll expand the expression using the binomial expansion and then find the derivative of each term. Therefore, the derivative of f of x with respect to x is equal to 3 into x squared minus 6x plus 9. However, differentiating such functions with higher powers is quite tedious. For example, how will you find the derivative of x minus 3 whole raised to the power 50? Such functions can be differentiated by using the chain rule. F is a real-valued function, which is a composite of two functions, u and v. Suppose t is equal to v of x, and if both dt by dx and du by dt exist, then df by dx is equal to du by dt into dt by dx. The chain rule can be also applied to functions that are composites of more than two functions. That is, if f is a real-valued function which is a composite of three functions u, v, and w, then the derivative of function f is as shown here. Now, let's apply the chain rule to differentiate f of x is equal to x minus 3 whole raised to the power 50 with respect to x. Clearly, function f is a composite function. Let's define the function as h circle g of x, where g of x is equal to x minus 3 and h of x is equal to x raised to the power 50. Suppose t is equal to x minus 3. This implies that f of x is equal to h of t, which is equal to t raised to the power 50. By the chain rule, the derivative of f with respect to x is equal to the derivative of h with respect to t into the derivative of t with respect to x. Thus, df by dx is equal to 50 into t raised to the power 49. On substituting the value of t, we get the derivative of f of x with respect to x is equal to 50 into x minus 3 whole raised to the power 49. Let's now find the derivative of another function. F of x is equal to sine x squared plus 1 by using the chain rule. Clearly, f of x is a composite function involving a trigonometric function and an algebraic function. Let's define the function as h circle g of x, where g of x is equal to x squared plus 1 and h of x is equal to sin x. Suppose t is equal to x squared plus 1. This implies that f of x is equal to h of t, which is equal to sin t. So, the derivative of f of x with respect to x is equal to dh by dt into dt by dx. On differentiating, we get 2x into cos t. On substituting the value of t, we get the derivative of f of x is equal to 2x into cos of x squared plus 1. Alternatively, its derivative can also be obtained by finding it directly. That is, on differentiating both the sides with respect to x, we get df by dx is equal to d by dx of sine of x squared plus 1. Now, by the chain rule, we get cos of x squared plus 1 into d by dx of x squared plus 1. The derivative of x squared plus 1 with respect to x is equal to 2x. Hence, the derivative of the given function is equal to 2x into cos of x squared plus 1. Let's now learn to differentiate functions involving two variables. Consider the equations y minus 2x is equal to 5 and y plus cos y is equal to sin x. Let's analyze each equation. The first equation can be solved for y and rewritten as y is equal to 2x plus 5. Such an expression, which can be easily solved for y and written in the form y is equal to f of x, is said to be y, is given as an explicit function of x. However, for the second equation, we do not see any easy way to solve it. Clearly, it is inherent that y is a function of x. Mathematically, a function that is formed implicitly is called an implicit function. Let's first find the derivative of y minus 2x is equal to 5. First, we'll express the equation as y is equal to 2x plus 5. The derivative of y with respect to x is equal to 2. Alternatively, we can also differentiate the equation with respect to x on both the sides. Thus, we have d by dx of y minus 2x is equal to d by dx of 5. We know that the derivative of a constant is 0. Now, by the property of derivatives, we get dy by dx minus d by dx of 2x is equal to 0. This implies that dy by dx minus 2 is equal to 0. Therefore, dy by dx is equal to 2. Next, let's differentiate the equation y plus cos y is equal to sin x. Such equations can be differentiated directly with respect to x. Differentiating both the sides with respect to x, we get d by dx of y plus cos y is equal to d by dx of sin x. By applying the property of derivatives, we get d by dx of y plus d by dx of cos y is equal to d by dx of sin x. By the chain rule, the derivative cos y with respect to x is minus sin y into dy by dx, and the derivative of sin x with respect to x is cos x. Taking dy by dx common, we get 1 minus sin y into dy by dx is equal to cos x. Therefore, dy by dx is equal to cos x divided by 1 minus sin y. Now, let's find the derivatives of inverse trigonometric functions. Beginning with the function f of x is equal to sin inverse x. Let y be equal to sin inverse x. This can also be written as x is equal to sin y. Let this be equation 1. Now, let's differentiate both the sides with respect to x. Using the chain rule, the derivative of sin y with respect to x is equal to cos y into dy by dx. This implies that dy by dx is equal to 1 divided by cos y. Let's write cos y is equal to the square root of 1 minus sin squared y. On replacing sin y with x, we get 1 divided by the square root of 1 minus x squared. Therefore, dy by dx is equal to 1 divided by the square root of 1 minus x squared. The derivative of sine inverse x is only possible in the open interval -1 and 1. Next, let us find the derivative of f of x is equal to cos inverse x. Let y be equal to cos inverse x. This can also be written as x is equal to cos y. Let this be equation 1. Now, let's differentiate both the sides with respect to x. We know that the derivative of cos y with respect to x is equal to minus sin y into dy by dx. This implies that dy by dx is equal to minus 1 divided by sin y. Let's write sin y is equal to the square root of 1 minus cos squared y. On replacing cos y with x, we get minus 1 divided by the square root of 1 minus x squared. Therefore, dy by dx is equal to minus 1 divided by the square root of 1 minus x squared. The derivative of cos inverse x exists only in the open interval -1 and 1. Now, consider the function f of x is equal to tan inverse x. Let y be equal to tan inverse x. This can also be written as x is equal to tan y. Let this be equation 1. Now, let's differentiate both the sides with respect to x. We know that the derivative of tan y with respect to x is equal to sec squared y into dy by dx. This implies that dy by dx is equal to 1 divided by sec squared y. Let's write sec squared y is equal to 1 plus tan squared y. On replacing tan y with x, we get 1 divided by 1 plus x squared. Therefore, dy by dx is equal to 1 divided by 1 plus x squared. The derivative of tan inverse x exists for all real values of x. In a similar manner, we can determine the derivative of cot inverse x. Sec inverse x and cosec inverse x. Take a look at these graphs. It is clear that the graphs get steeper as the value of x goes on increasing. Let's analyze the curve representing y is equal to x cubed. For different values of x, the values of y are as shown. Observe that the value of y increases with an increase in the value of x. Consider another function y is equal to x raised to the power 5. Here we see that as x increases from 1 to 2, f3 of x increases from 1 to 2 cubed, and f5 of x increases from 1 to 2 raised to the power 5. Observe that for the same increment in the value of x, f5 of x increases faster than f3 of x. This change is quite evident if we take higher powers of x into consideration. In general, the value of y is equal to fn of x increases as n increases for n is equal to 1, 2, 3, and so on. Such a statement is true for all positive values of n, where fn of x is equal to x raised to the power n. Here, we can say that the growth of polynomial function depends on the degree of the polynomial. That is, the higher the degree, the greater is the growth of the polynomial function. Now, look at another function y is equal to f of x is equal to 3 raised to power x. Here too, an increase in the value of x from 1 to 2 implies an increase in the value of f of x from 3 to 3 squared. Observe that function f of x increases faster than function f3 of x, with an increase in the value of x from 1 to 2. Thus we can say that for any positive integer n and for any positive value of x, the increase in f of x is equal to n raised to the power x is larger than the increase in fn of x is equal to x raised to the power n. In all the functions, the graphs grow as the value of x increases. Such types of functions are called exponential functions. Mathematically, an exponential function with a positive base b greater than 1 is a function defined by y is equal to f of x is equal to b raised to the power x. Exponential functions with base 10 are called common exponential functions. For example, f of x is equal to 10 raised to the power x is a common exponential function. Exponential functions with base e are called natural exponential functions, where e is equal to the sum of the series 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial, and so on. F of x is equal to e raised to the power x is an example of a natural exponential function. Do make a note of some features of exponential functions. The domain of exponential functions is the set of all real numbers. The range of exponential functions is the set of all positive real numbers, Graphs of exponential functions always grow upwards as we move from the left to right on the x-axis. Graphs of exponential functions are close to the x-axis, but never touch it for any large negative values of x. Point 0, 1 is always on the graph of any exponential function. This is because b raised to the power 0 is always 1 for any real number b greater than 1. Let's consider an exponential equation b raised to the power x is equal to a, where b is a real number greater than 1. In logarithmic form, this can be written as shown here. This is read as logarithm of a to base b is equal to x. Mathematically, for a real number b greater than 1, the logarithm function is defined as log of a to base b is equal to x if b raised to the power x is equal to a. Take a look at the logarithmic forms of some exponential expressions. Clearly, we say that the logarithm is a function from positive real numbers to all real numbers. In other words, the logarithmic function log to base b is a function from positive real numbers to real numbers such that for all x belonging to the set of positive real numbers, there exists a real number y such that log x to base b is equal to y if b raised to the power y is equal to x. Logarithms to base 10 are called common logarithms. Logarithms to base e are called natural logarithms. For convenience, we do not write the base of natural logarithms. In other words, if the base is not mentioned, then it is considered as e. The figure here shows the graphs of logarithmic functions to the base 2, e, 3, and 10. Note some facts about logarithmic functions. The logarithm of a non-positive number cannot be defined. Hence, the domain of a logarithmic function is the set of positive real numbers. The range of a logarithmic function is the set of all real numbers. Point 0, 1 is always on the graph of any logarithmic function. Graphs of logarithmic functions grow as we move from the left to right on the x-axis. Graphs of logarithmic functions are close to the y-axis, but never touch it for any small positive values of x. Graphs of y is equal to e raised to the power x and log x to the base e are mirror images of each other reflected in the line y is equal to x. Let's now see some important rules of logarithms. The change of base rule states that log p to base a is equal to log p to base b divided by log a to base b. Let's verify this. Let log p to base a be alpha, log p to base b be beta, and log a to base b be gamma. This implies that a raised to the power alpha is equal to p, b raised to the power beta is equal to p, and b raised to the power gamma is equal to A. From equations 1 and 3, we get P is equal to B raised to the power gamma into alpha. Now, from equations 2 and 4, we get B raised to the power beta is equal to B raised to the power gamma into alpha. This implies that beta is equal to gamma into alpha. Alpha is equal to beta divided by gamma. Therefore, log P to base A is equal to log P to base B divided by log A to base B. Let's look at the relations y is equal to e raised to the power minus 2x. Y is equal to sine of e raised to the power x, and y is equal to cos of log x. Clearly, these are composed of exponential and logarithmic functions. To differentiate such relations, we use some basic formulae. The derivative of e raised to the power of x with respect to x is e raised to the power of x. In other words, the derivative of a natural exponential function is the function itself. The derivative of log x with respect to x is 1 divided by x. Let's apply these formulae to find the derivatives of the given relations. Observe that in each case, the given function is a function of a function. So, we will apply the chain rule while differentiating them. Let's begin with the first one. On differentiating both the sides with respect to x, we get dy by dx is equal to d by dx of e raised to the power minus 2x. By applying the chain rule, the right-hand side becomes e raised to the power minus 2x into d by dx of minus 2x. The derivative of minus 2x with respect to x is minus 2. Therefore, dy by dx is equal to minus 2 into e raised to the power minus 2x. Next, let's find the derivative of y is equal to sine of e raised to the power x. Differentiating both the sides with respect to x, we get dy by dx is equal to d by dx of sine of e raised to the power x. By applying the chain rule, the derivative of sine of e raised to the power x with respect to x is equal to cos of e raised to the power x into d by dx of e raised to the power x. The derivative of e raised to the power x with respect to x is e raised to the power x. Therefore, dy by dx is equal to e raised to the power x into cos of e raised to the power x. Lastly, differentiating both the sides of y is equal to cos of log x, we get dy by dx is equal to d by dx of cos of log x. By applying the chain rule, the right-hand side becomes minus sine of log x into d by dx of log x. The derivative of log x with respect to x is 1 divided by x. Therefore, dy by dx is equal to minus 1 divided by x into sine of log x. Many a times, we have to find the derivative of a function that is the power of another function. Such functions can be differentiated easily by applying logarithms on both sides. Taking logarithm of the function, we get log y is equal to v of x into log u of x. Now, the right-hand side obtained is the product of two functions, which can be solved easily by applying the product rule. On differentiating both the sides, we get d by dx of log y is equal to d by dx of v of x into log u of x. Now, by applying the chain rule, the derivative of log y with respect to x is 1 divided by y into dy by dx. Thus, the derivative of the right-hand side is equal to v of x into 1 divided by u of x into u dash of x plus v dash of x into log u of x. Therefore, the derivative of y with respect to x is as shown here. This process of differentiation is called logarithmic differentiation. Note that this method is applicable only if functions f of x and u of x are positive, because logarithms of negative quantities are not defined. Logarithmic differentiation can be applied to find the derivative of any complex function. Hence, we can say that logarithmic differentiation is a process by which a complex function can be differentiated by taking logarithm to base e of the function and then differentiating both the sides. Let's apply logarithmic differentiation to find the derivative of y is equal to sin x whole raised to the power log x. First, take logarithm to base e on both the sides. This gives log y is equal to log x into log of sin x. Next, differentiate both the sides with respect to x. This gives d by dx of log y is equal to d by dx of log x into log of sin x. By applying the chain rule, the derivative of log y with respect to x is 1 divided by y into dy by dx. The right-hand side is the product of two functions, log x and log of sin x. So we use the product rule to differentiate it. This gives the derivative of the right-hand side equal to log x into 1 divided by sin x into cos x plus 1 divided by x into log of sin x. Therefore, the derivative of y with respect to x is equal to y into log x into cot x plus 1 divided by x into log of sin x. Consider two relations, x is equal to at squared and y is equal to 2at. Clearly, variables x and y do not have a direct relation. However, they depend on a third variable, t. Thus, we can say that the relation between variables x and y is expressed via the third variable, t. This third variable is known as the parameter. Expressing a relation between two variables, x and y, in the form of x is equal to f of t and y is equal to g of t is said to be its parametric form, with t as the parameter. If we have to find the derivative of y with respect to x, then we use the chain rule. Therefore, dy by dt is equal to dy by dx into dx by dt. This implies that dy by dx is equal to dy by dt divided by dx by dt, provided dx by dt is not equal to 0. Or dy by dx is equal to g dash t divided by f dash t, where g dash t represents dy by dt and f dash t represents dx by dt. We notice here that dy by dx is expressed in terms of the parameter, and it does not directly involve the main variables x and y. Let's now find the derivative of the relations considered earlier and find dy by dx. The derivative of x is equal to at squared with respect to t is equal to 2at. The derivative of y is equal to 2at with respect to t is equal to 2a. Now, dy by dx can be written as dy by dt divided by dx by dt. This is equal to 2a divided by 2at, which is equal to 1 divided by t. Let us consider one more example. Consider the relations x is equal to sine 2 theta and y is equal to 2 cos theta. It is clear that the variables x and y are expressed in terms of a third variable, theta. Thus, both the relations are in parametric form where theta is the parameter. Differentiating x is equal to sine 2 theta with respect to theta, we get cos 2 theta into 2, which is equal to 2 cos 2 theta. Differentiating y is equal to 2 cos theta with respect to theta, we get 2 into minus sine theta, which is equal to minus 2 sine theta. Now, dy by dx can be written as dy by d theta divided by dx by d theta. Therefore, dy by dx is equal to minus 2 sine theta divided by 2 cos 2 theta, which is equal to minus sine theta divided by cos 2 theta. Consider a function y is equal to f of x. We know that the derivative of y with respect to x is equal to f dash of x. If we differentiate f dash of x with respect to x again, then it is called the second order derivative of y with respect to x. However, the second derivative exists only if f dash of x is differentiable. The second derivative of y with respect to x is denoted as shown here and read as d squared y by dx squared, or d squared y, or y double dash, or y2. The second order derivative of f of x is denoted as shown and is read as f double dash of x, or the second order derivative of f. We use these notations according to our convenience. Similarly, other high-order derivatives are also defined. Let's find the second-order derivative of y is equal to x squared plus ax cubed. Differentiating both the sides with respect to x, we get dy by dx is equal to 2x plus 3ax squared. Differentiating both the sides with respect to x again, we get 2 plus 6ax. Therefore, the second order derivative of y with respect to x is equal to 2 plus 6ax. Next, let's find the second order derivative of y is equal to 2x cubed into sin x. Let's first differentiate both the sides with respect to x. Clearly, the right-hand side is a product of two functions. By the product rule, we get 2x cubed into cos x plus 6x squared into sin x. differentiate both the sides with respect to x again. Here we have the sum of the product of two functions. So, we differentiate each term by applying the product rule as shown here. On rearranging the terms, we get this expression. Therefore, the second order derivative of y with respect to x is equal to 12x minus 2x cubed into sin x plus 12x squared into cos x. Take a look at the graphs of a parabola and a sine function. It is clear that the functions f of x and g of x are continuous in the closed interval a, b. Let's now draw tangents to the curves at various points. Observe that the parabola has only one tangent parallel to the x-axis. On the other hand, the sine graph has two tangents parallel to the x-axis. Since the tangents are parallel to the x-axis, their slopes are 0. That is, in each of the graphs, the slope becomes 0 at one point at least. On the parabola, let C be the point where the slope is 0. This means the derivative of the function with respect to x at x is equal to c is 0. Observe that the values of the function at points a and b are equal. This leads us to an important theorem on calculus, which is known as Rolle's theorem. It states that if a function f from a closed interval a, b belonging to the set of real numbers is continuous on the closed interval a, b and differentiable on the open interval a, b, such that f of a is equal to f of b, where a and b are some real numbers, then there exists some real number c in the open interval a, b, such that f dash of c is equal to 0. This theorem claims that the slope of a tangent at any point on the graph of y is equal to f of x is the derivative of f of x at that point. Consider a function y is equal to f of x, which is continuous on the closed interval a, b and differentiable on the open interval a, b. The values of the function at a and b are not equal. Clearly, Rolle's theorem is not satisfied. However, this extends Rolle's theorem to an important fact, which is known as the mean value theorem. The theorem states that if a function f from a closed interval a, b belonging to the set of real numbers is continuous on the closed interval a, b and differentiable on the open interval a, b, then there exists some real number c in the open interval a, b such that f dash of c is equal to f of b minus f of a whole divided by b minus a. The mean value theorem is denoted by MVT in short. Let's look at its geometrical interpretation. Draw a secant and a tangent to the curve as shown. We know that f dash c is the slope of the tangent to the curve y is equal to f of x at the point c, f of c on the curve. It is clear from the figure that the slope of the secant is given by f of b minus f of a whole divided by b minus a. Now, the MVT states that there exists some c in the interval a, b such that the slope of the tangent at point c, f of c is equal to the slope of the secant drawn on joining the points a, f of a and b, f of b. In other words, there exists some c in the interval a, b such that the tangent at the point c, f of c is parallel to the secant that joins the points a, f of a and b, f of b.